Hello again. Continuing our work through the Thermodynamics and Chemistry 1 worksheet, we're going to look at problem 2 now, which is a constant volume calorimetry, or a bomb calorimetry problem with a separately assigned C-cal. So it depends on how you're looking at this. This one is a separate C-cal, sorry. So what they're telling us is that we have a bomb calorimeter now, which remember is an enclosed constant volume kind of a vessel. And they're telling us that inside this thing, I have 4.40 grams of glucose. All right, I'm going to burn that in there. And the calorimeter also has in it 800 grams of water as the medium that's carrying the heat around. And the temperature is increasing from 15.0 degrees C up to 18.7 degrees C. All right, and so we have this change of 3.7 degrees C as our temperature change. Just so you can picture this, I'm not burning the glucose in water, right? A bomb calorimeter typically has some sort of a vessel that's got the liquid in it. In this case, it's the water. And then underneath it somewhere, I would have some sort of a little sample container with some sort of a little ignition device that when I burn that sample that's sitting on here, the heat goes up and heats up the water, and I'm measuring the temperature of the water using a thermometer like that. The outside of a bomb calorimeter is insulated. And so one of the kind of presumptions that we make is that we don't actually exchange any heat with the environment. And depending on the quality of your calorimeter, that may or may not be true, but it's often true, or pretty close to true. They tell us that the heat capacity of the calorimeter, so C-cal, is equal to 550 joules per degree C. All right, what is the value of Q for the combustion of the glucose sample? All right, so now in this case, we're going to be using the equation that'll say that the Q of the reaction, so the energy that's coming out of this reaction, is the opposite of the energy that's being absorbed by other stuff. Right, equal energy because we're not losing any to the environment. So whatever comes out of the glucose will be absorbed into the water and the walls of the calorimeter. And so we have to consider both here, Q of the water and Q of the calorimeter. Typically in a constant pressure calorimetry, we're going to lump these together. In constant volume calorimetry, oftentimes you'll see them listed separately. And so here we've got Q of the water. Well, I can say that's going to be mass times C times delta T, where C here is the specific heat of water. And so this is all, I'm just going to label down here, all for water. And then Q of the calorimeter is going to be my C-cal times the delta T. Okay, so that's the calorimeter part. Okay, I've got some values here. So Q of the reaction then equals negative, gigantic parentheses, mass of the water they gave me at 800 grams. Okay. The specific heat of water is one that you will likely end up memorizing just because you'll use it so much. And it's 1 calorie per gram degree, or 4.184 joules per gram degree. And that was the number given to us in this problem. And the temperature change for this was 3.7 degrees, right? Big old plus sign so I don't lose it. C-cal, they said, was 550 joules per degree times the increase in temperature of the calorimeter. I got too close with my bracket. That's also 3.7 degrees. All right, so both the calorimeter, the container, and the water in it went up by the same temperature. And so I'm using the same delta T in both cases. All right, so when I do the math on this thing now, I'm going to have 800 times 4.184 times 3.7. So that gives me 12,384.7 3.64. What are my units? Well, my grams canceled right there. My degrees canceled right there. So I've got joules left over for my unit. That's the water part. Plus my 550 joules per degree times 3.7. Again, look at the units. My degrees cancel like that. So I again have joules, which is good because if I want to add them together, they had best have the same units. It comes out to 2035. I add those numbers together. 12,384.64 plus 2035 gives me 14,419.64 joules. And don't forget the negative sign. Okay, so typically we would round that. Well, we definitely will round this for significance. We look back at our starting numbers, and here's where I'm going to presume that the way the problem was written, that they had a little bit of a typo. So why? Well, if I go back and I look at significant figures, let me do this in, let's go purple here. My glucose number had 3 significant figures, right? 4.40. My temperatures all had 3 significant figures. But the way that they wrote my number for the mass of water, it's written in the problem as 800 G. That only has 1 significant figure, guys, right? Just the 8. So that would mean that I would have to round my answer, frustratingly, to just a single significant figure. I would round to 10,000 joules. I don't think that that's what they intended. I think that when they wrote the problem, they intended to use this annoying chemistry thing that we do for significant figures to say the decimal point now makes that all 3 of those digits significant, right? The rule for significant says if there's a decimal point, trailing zeros count. And so I believe that they intended that 800 to actually be 800 point, 3 significant figures. So I'm going to choose to interpret it that way. Round it to 3 significant figures and say Q of the reaction is negative 14.4 joules or 14.4 kilojoules. Okay, and that's what this problem asks. What is the value of Q for the combustion of this glucose sample? So that's it. Again, if we wanted to normalize it to figure out the combustion of glucose, right, in general, we could say, and I've run out of room here, so I'm going to pop to a new page. We could say we liberated 14.4 kilojoules from 4.40 grams of glucose. Right, now we're going to get a normalized number. So we take our 14.4, we divide it by 4.4, and we get 3.27 kilojoules per gram. That it would be maybe a very typical number that would be written in a handbook somewhere. How much energy per gram? And that's totally appropriate. We could also do it per mole, where we would just convert that 4.40 grams to moles based on formula weight, and then divide by that number. We also could talk about a different energy unit. Now, I only used kilojoules because that's what was in the problem. They gave me joules, and so I stayed with that unit. But I could just as easily have done a conversion into the calorie unit. And remember our conversions here, that basically we've got 4.184 joules is equal to 1 scientific calorie. And so, of course, I can make those both 1,000 times bigger, make it kilojoules per kcal. But I also know that 1 kcal is equal to 1 dietary calorie. And so if I do this math, and I do 3.27 divided by 4.184, I'm going to get 0.78 782, I guess, kcals per gram of glucose. Okay, now that is not what you've been trained to learn from your nutrition labels, that every gram of carbohydrate provides 4 dietary calories, 4 calories per gram. This is a different number. So we could say, well, why is this a different number? And that's a fantastic question, right? Probably because this problem wasn't written with the idea of using accurate numbers in that sense. I don't think they intended us to go this direction with it. But I just wanted to show you an example of how we can convert these units, right? Our initial problem ended us with kilojoules for the sample, which is all the problem was asking for. And that's totally fine. If we needed it in a different unit, we could have converted it. Kilojoules per gram or kilojoules per mole would be absolutely appropriate answers if we wanted to get that kind of unit rate sort of a thing. Alternately, we can convert it into the calorie sorts of units, either by doing this or by, oops, that's not the button I wanted. I apologize. How do I go back? There we go. If we had gone back to this page and replaced this right here with 1.00 calories per gram degree Celsius, that would have been the specific heat of water in calories. We then also would have had to know the calorimeter constant in calories, which we didn't have. The point is, we can convert back and forth as needed between these energy units using the, I think does not want to scroll for me. There we go. Using these conversion factors. You can do that for any of the energy stuff that you're trying to do. All right, so with that, I'm going to end this video and say keep up the great work and watch the next video in the series for problem 3. Take care.